Good morning, everyone. I would like to begin with a brief outline of how this presentation is going to go. First, I'll give a brief introduction to the subject matter, and the bulk of the presentation will consist of some live demos of Design Studio and showing how it can work with structural optimization problems. And finally, I'll finish up with just a few concluding remarks. So the title of this webinar is Structural Optimization with Design Studio. So the first question is, what is optimization? Optimization is a process where we are given a set of a design space defined by a set of design variables. And we want to find the objective function, that the set of design variables that minimizes some objective function with the possibility of having to also satisfy constraints. In structural optimization, it means that the design variables are going to control the layout of the structure. It can be things like dimensions or sizes that define how we can build some particular structure. The objective function and constraints are going to come from responses from a structural analysis. And they could include anything from mass or volume to responses like stress, displacement, eigenvalue. The next question is, what is Design Studio? VR&D has a program called Genesis, which is our structural optimization software. Genesis is a batch program, which means it takes its input from an input file and does its calculations and produces a set of output files. So Genesis does the actual structural optimization. Design Studio is a graphical interface that sort of wraps around Genesis and makes it convenient to set up the design data and also to visualize the results of the optimization. Design Studio is task-oriented. When we look at the interface, we'll see that it's broken up into a set of trails or wizards, which sort of guide you through the process of creating any data required to set up the problem that you want to set up. Design Studio is designed to be as non-modal as possible. That means you can switch back and forth in different trails to edit different data simultaneously. And finally, Design Studio is designed to work with a finite element model of the structure, and it will show the structure there so that you can easily select quantities like grids or elements to create the data necessary to set up the design optimization problem. The optimization types available in Design Studio are the same as what we have in Genesis. The analysis options are linear statics, eigenvalues, frequency response for dynamics. The optimization options are divided into different categories based on what the design variables are actually going to design. And we have 6 different types of optimization in Design Studio and Genesis. So what I would like to do next is go through each one of these optimization types and work an example problem of that type in Design Studio. So the first optimization that I would like to consider is topology optimization. Topology means that we are going to be given a design space which is going to be filled with elements, and our goal is to try and select the fraction of the elements within this design space that will be the best for our particular objective. And the objective could be to make a stiff structure, or it could be to, say, maximize some natural frequency. But we have to define some objective, and we want to find what fraction of elements and where in that design space to put those elements to optimize our objective. So at this point, I would like to break out of the PowerPoint and go into Design Studio. Before I get into the topology problem, I'd like to take a few moments to just explore the Design Studio interface itself. When Design Studio comes up, we see that it's divided into 3 windows. The main window, the largest window, is the Design Studio viewport. This is going to show us an image of our finite element model. And we have controls here to change the view direction. We can zoom in and zoom out, or we can pan the model around. We have controls to zoom into a particular region of the model, or we can go back and fit the model to the view, or we can choose one of the standard orthogonal views or standard isometric views. This is the Design Studio viewport. Below that, we have the Messages window. This is where Design Studio will print any detailed information that we request. The main window on the side has the menu bar, and its main area is divided into a set of tabs which represent the different areas of control, or the different types of data that are going to be worked on within each area. And we're free to switch among the different tabs at will. The Display tab lets us control how things look in the viewport. For example, at the bottom, we have buttons to control how we're going to actually draw the finite element model. We can choose a plain wireframe view, or we can choose to show only feature lines, or we can have a shaded model with feature lines, or we can actually choose to show the flat shaded model with the element outlines drawn as well. We can choose a transparency option if we need to see through the model. We have a ruler option if we need to quickly see dimensions of the model. We can measure things on the screen with the ruler. The different colors in the model mean that these elements are all associated together, and we call these associations groups. In the Display tab, we have a control to show and hide the different groups. We can turn groups off in order to only focus on a smaller part of the model. We can choose either from the list or from the screen itself. We can similarly show and hide individual elements. Another function on the Display tab is to identify. We can identify grids. If we click on a grid, the Messages window will give us some information about the chosen grid, and the grid is highlighted in the model, in the viewport. Similarly, we have Identify Elements. We can click on an element, and the Messages window will give us detailed information about that element, including what group that it's a member of and the grids that that element connects to. Design Studio has analysis preprocessing as well. We don't actually intend for Design Studio to be used as your primary analysis preprocessor. We're focused on the design data, but it does have capabilities to do analysis preprocessing. For example, we can look at the load cases. We can see, if we select one, we see the boundary conditions highlighted as well as the static load applied. This particular problem has 3 load cases set up. We could choose to edit a load case, in which we can change its label, or we could change boundary conditions, we could change the output requests. Now I'd like to get into the topology optimization part. For this problem, we have the 3 static load cases, and we want to use all 4 of these groups, the 2 solid parts and the 2 shell parts, as our design space. The blue members at the end, where the boundary conditions are attached, are not going to be designed. So we are fixing those. Those elements are required to be present. And from the design space, we want to choose the best 20% of the elements to make the stiffest structure possible under those 3 static load cases. So the first thing we will do is go to topology regions, where we will define which groups are going to be designed with topology. In this case, we can choose 4 groups, and we push the Modify Topology Design button. The only information we really need to specify to define a topology region is the initial mass fraction, which is going to be the same as the percentage of elements that we want to keep in the final optimal design. And in this case, we want to keep 20%. So we can finish. Now, when we look at the list, these elements that we just added the topology design to have a new icon next to the property. This little hammer icon indicates that this property is being worked on. It has design data associated to it. In the optimization problem, there were 3 parts. If we remember from the first slide, what is optimization? We have design variables, we have objectives, and we have constraints. So the topology region essentially defines all of the design variables for the topology problem. Next, we need to define the objective function. To make a stiff structure, mathematically, we're going to say we want to minimize the strain energy associated to the given load cases. Strain energy, if you think, is proportional to the load times the displacement. And since the loads are constant, and minimizing the strain energy is the same as minimizing the displacement under those loads. So that corresponds to the stiff structure. To create that in Design Studio, we simply push the new topology objective button. Strain energy was already selected for us, and minimize is selected. So we simply need to select the load cases that we want to consider for these objectives. And in this case, we want to consider all 3 static load cases. When we finish, now the list shows the 3 topology objectives for the load case, and the target is to minimize, and they all have a weight factor of 1. When we're working with multi-objective problems, such as this one, we have the possibility to weight some particular objective more important than others. In this case, we're going to give equal weighting. Finally, for topology optimization, the most common constraint is simply a mass fraction constraint to tell the optimizer to limit the amount of material that it can use. If we don't give any mass fraction constraint, then of course the stiffest structure possible is simply going to use all the material available. We don't want that case. We want to find the best 20%. So we will put an upper bound of 0.2 with the mass fraction response type, and we will select the individual groups that have the topology design and finish. And now we have our topology constraint. The next step is to solve the optimization problem. And we have 2 different possibilities for that, depending on a given site's installation of Design Studio and Genesis. In some cases, Design Studio and Genesis will be installed on the same machine. In that case, we can simply go from Design Studio to the Genesis menu and say Optimize. This will tell Design Studio to export the Genesis input file containing all of the data that we have specified in our Design Studio interface. Design Studio would then launch Genesis in the background and wait for it to finish, and then give us the opportunity to load the Genesis output files. Other installations might not like to run Genesis on the same workstations where they're using Design Studio, but rather they would have Genesis installed on a server machine. In that case, we can go to the File menu and say Export Input Data to write out the Genesis input file ourselves. We would then send that input file to the server machine and submit the Genesis job and bring back the Genesis output files, where we can then load them into Design Studio manually. For this problem, this is a small problem, but still on this machine I'm using here will take a few minutes to run, and rather than stop the webinar for a few minutes while this problem runs, I'm going to pretend like I already run the problem before, and I'm going to simply go and load the output results that I have previously generated. For topology, we're going to get an output file with the DENS, the topology density, which is the standard name for the topology design variables. Once we've loaded the post-processing file, we can go to the Post tab to visualize the results. And with topology results, we really have two ways we can look at this. The first is to go to the Deform Mesh Color Mesh, and we will choose to color the mesh with the topology variable values. And in the topology variable is simply a value that goes from 0 to 1, where 0 means topology optimization told us we don't need that element, and 1 means that element is very important and we must keep that element. So in the plot, we can see the blue elements need to be taken away, and the red elements are the elements we should keep for the optimal answer. And the gray elements are the ones that were not designed, so those are going to stay because they were not designed at all. Of course, with this shell mesh, we can see on the shell surface the topology answer very nicely. But with the solid block, we see we get blue over most of the surface of the solid, and it's hard to see inside to see what the topology is actually telling us. And Design Studio can help us with that. If we go to Options, we can actually mask off the low value elements, so we only see the higher values. And this will show us very clearly exactly what elements the topology optimization is keeping for the solution to this problem. Another way to visualize the topology results is to go to the density isosurface. If we show the density isosurface, it's going to be similar to masking off the low-valued elements, but now we're going to put a smooth surface enclosing all of the higher density-valued elements. So we see the solution as more like what a finite element model of the topology answer would look like. And we can go to Options here, and we can change the isosurface value, which is where we're going to make that contour. We also have an option to show the original design space with the gray highlight. If we go back to the Display tab, we have an option to do a model cutaway. We can cut the model along some particular plane, and we can interactively slide a slider so we can see inside it to see what the topology answer is looks like in detail. And we can choose to cut along a different axis. That's another way to visualize the result. So this is what I wanted to show for the topology optimization problem. At this point, I'd like to go to the next type of optimization, which we call sizing optimization. Sizing means that we are going to design the property values on the one- or two-dimensional elements. These types of elements have real numbers on their properties that define the missing dimensions. For example, shell elements have a thickness value, or the bar elements have dimensions to define the cross-section. And those values can be designed by optimization. So now I'll go back to Design Studio and look at a sizing optimization problem. So here we have a simple model of a pallet lifter. This model has a load case defined. It has a boundary condition at the top and some pressure load along the lifting arms. And what we would like to do is design the thickness of these shells to minimize the total mass of the part. Normally in structural design, we can say that the cost to produce the part is proportional to the mass. That's a very common assumption. And so if we minimize the mass, it's the same as minimizing the cost. This particular part has two different materials, an aluminum material and a steel material. And we actually only want to design the shells associated to the aluminum material. So to set up the sizing problem, we will go to the Design tab, and we will go to the Quick Setup Trails. For shell sizing optimization, we have a quick sizing setup, which will make it very convenient to set up the design variables and associate them to the properties. So what we want to design here is just the piece shell properties that are using the aluminum material So I'll use the find filter to filter the list to just show those properties to make it very easy to select them all. These are the properties that I want to design. Next, I need to choose the design variables that are going to be assigned to each one of these shells. And we have some functions here to let us easily design the initial value, the upper bound, and the lower bound of these design variables. These can be either constant values or some multiple of the current thickness. And the current thickness is the thickness that's defined on the piece shell property itself. So for the initial value, I want to use the current thickness. So I'll leave the constant to 0 with a multiplier of 1. But for the lower bound and upper bound, I want to use constant values. I want to say the lower bound is 0.1 with the 0 multiplier and an upper bound of 2 with the 0 multiplier. And then I'll say finish. And now the summary at the bottom here is telling us we now have 8 design variables defined and 8 sizing regions defined. So we can change to the design variables category and we see the list of these 8 design variables. And we can see that they all have different initial values because the initial value came from whatever the piece shell property itself said was the thickness. That's going to be the starting thickness when we run optimization. But the lower bound and upper bound are all the same because we chose to use constant values. Next, we would like to set up the objective and the constraints. In this problem, the objective is simply going to be minimize the mass, which is handily already selected for us. The constraints, we want to set up two kinds of constraints in this problem. One is going to be a stress constraint, because we want to make sure that the part doesn't break under the loading. And second, we want to apply some displacement constraint to ensure that under the load, that the ends of the pallet lifting legs don't deform too much. So first we will create the stress constraint. We're going to give an upper bound, 20,000 psi on the von Mises stress of these designed shell elements. So we'll set the upper bound, we'll choose stress. We need to select the design elements. These are already selected. If they weren't selected, we could also filter the list to show us only the properties that are currently associated to sizing data, and we can select those. We want to select von Mises top and bottom, means the top of the shell surface and the bottom of the shell surface. And finally, we choose the load case. And we finish, and now we can see we have two constraints. Actually, we made one separate constraint for the top surface von Mises stress and another for the bottom surface on Mises stress. We would like to create a second constraint of displacement. We want to put a total displacement magnitude of 0.1 inches, the total translation, and we want to choose grids at the tips of the pallet lifting legs. So we want these 4 grids to have this total translation magnitude for the static load case. So now we can see the 3 constraints that we have defined, the stress and the displacement. So now we're ready to run the optimization in Genesis. Again, we can either run directly if we have Genesis on the same machine, or we can export the input data, send it to the server. I've already run this problem, so I'm simply going to go straight to import the results. The kind of results that we get with sizing, we write out a file called some project with the OPOST word. OPOST stands for optimization post, which is going to have, in this case, shell thicknesses. So if we choose one of these results, we actually will color the model according to the thickness of the individual elements. And we can see that for the different properties that were defined, all of the elements in that given property have the same color because they all have the same thickness. With the value chosen, that means the color corresponds to the actual thickness value. But in looking at the optimization results, it can be useful to change to, say, value divided by original. This will give us how the thickness changed as a result of the optimization process. And now our scale goes from 1 to about 0.5, and the 1 value is these 2 shells that were the steel materials that were actually not designed. So the thickness of those did not change, which is why the current thickness and the original thickness value makes a ratio of 1. All of the other thicknesses actually decreased in value, which means that our initial design was over-designed, and we were able to reduce the mass in order to make our objective improve. We can actually go and load up the history file of this optimization run to see exactly how the mass changed. We get, for the design history, we get a plot that shows how the objective changed in each design cycle. And we can see the initial mass value and the final mass value. In particular, it's easy to look at the normalized value, and we can see that the final mass is around 75% of the initial mass. And the constraints started out well satisfied, and during the optimization process, they, of course, stayed well satisfied. So we were able to take out around 25% of the total mass, and we can see our new thicknesses for the particular part. If we want to see the actual values, we can show the thickness value, and we click on an element, and the messages window shows us the actual thickness value for that particular part. And we can look at the different properties and see the different thickness values. Another way we have to visualize the sizing results in Design Studio is to have Genesis write what we call the SSOL file, which we can then load in Design Studio. SSOL stands for shell to thickness, to solid. So that means that we're going to take shell elements and convert them into solid elements that reveal the actual thickness that those shells were trying to model. So now we can look at the structure and see thicknesses exposed. And we can zoom in on an area, and we can see the different thicknesses. And we see that this is not actually a conforming solid mesh. We simply took each shell element and expanded it into a solid element in the appropriate direction. So this is not a model that we can use for analysis, but it's nice for visualization. We can see exactly where the thick shell parts are and the thin shell parts. So that finishes up the sizing example. So the next type of optimization that I would like to consider is what we call topometry. Topometry is really a very special instance of sizing, but instead of forcing all of the elements in a given property to have the same thickness value, we're going to split it so that every single element in the design property is allowed to have its own independent design variable. This will essentially greatly increase the design freedom and hopefully give us the optimum answer, because we have maximized the design freedom. So let's switch back to Design Studio and take a look at a topometry problem. My computer will cooperate. It comes up. Okay.
You're only showing
So now we will look at the same sizing problem that we had before. Now what we want to do is use topometry, which means we're going to split the design variables so that every single element can be designed independently. If we look at the sizing category, we see we have the same sizing that we had before. Now we go to topometry. The only properties listed here are the ones that already have sizing data, because we cannot add topometry unless we already have sizing data. In this case, we want to do topometry on all of these sizing design properties. The information we need to specify for topometry includes potentially coarsening the topometry. If we choose no coarsening, it means that every single element will get its own design variable. Or we have the option to group adjacent elements into clumps to reduce the total number of design variables that we might create. We also have the possibility of enforcing certain symmetries. For example, in this case, we might want to force the final result to have a symmetric about this coordinate system, the YZ plane. So we can create a mirror YZ symmetry constraint. We say finish, and now we get the hammer icon in the topometry, which means these groups have topometry optimization. That's really all that's required to set up topometry. We already have the objective and constraints from the sizing problem. So the only thing topometry adds is to split the sizing design property. So then we would run Genesis, and now I will go and import results. Which we can then go back to post and look at the same way we looked at the sizing results. We can color the elements according to the thickness. And now we see a much different picture from the sizing result. Because now we're not getting a constant color across all the elements in a given property because we're doing topometry, which means every element is now independently designable. And we see that if we change to thickness by original, we see a different picture here. Now, the 1.0, the non-design part is still there, but many, many elements reduced below the 1.0, all of the blue part, but some elements actually increased in thickness, which we did not see before. But by giving this extra design freedom, we're allowing some elements to get thicker, whereas the majority of the elements in the part get thinner, and overall, we reduce the mass. And we can load the history file for this example, and we can see the total mass for the topometry actually went down to about 65% of the original. Whereas with the sizing alone, we only got to 75%, a 25% reduction. Here we're getting 35% reduction. So the topometry is actually giving us a better answer, which of course should be expected since we have added more design freedom. We've increased the number of design variables. So that's what I wanted to show for topometry. Now I'd like to switch to shape optimization. Shape optimization means that we are going to design the locations of the grids that define the spatial dimensions of the finite elements themselves. So this can be used for all types of finite elements, shell, solid, bar, but it's particularly useful for the solids. Because solid elements don't have any real numbers on their properties, there's no sizing optimization available, but they, of course, can be designed with shape optimization. So now we will go back to Design Studio and take a look at a shape optimization problem. To set up shape optimization, we need to define how the grids can move when design variables that define the grid location change. And we do that by creating what we call perturbations. A perturbation, you can imagine, is like a load applied to some particular grid, and that's going to be scaled by the design variable. And so as the design variable scales larger and larger, we push that grid in a particular direction farther and farther away. To help you create perturbations on all the grids in a structural model, we have a concept called domains. So primarily when you work with shape optimization, you're going to be creating domains and then perturbations on the control grids of the domains. In this particular model, this is a truck frame, and I want to design the location and size of these crossbars. So for now, I'm going to hide some of the actual structure, because when I already have these blue boxes, which are some domains that were already created. And in this demonstration, I'm simply going to create one additional domain to show how the process goes. So we will use the domain quick setup. We need to choose a group, and we will, in this case, pick the existing grids because we want the domain to attach to the domains that we already have. So for the hexa, we simply click the 8 corners, and we make a new candidate domain box. We can inspect it. Everything looks good. So we will accept that and say finish. So now we've created this new domain. Next, we need to create some perturbations on the control grids of this domain. We already have some control grids for some of the other domains. For example, this one, if we look, we can see we have some arrows here for this domain box to control the location of that crossbar that was inside that domain. Or we have arrows to control the width of that crossbar, or to control the height. And what I would like to do now is create some equivalent perturbations on this new domain box that I just made. So to do that, I'll go to New, Shape Morphing Set. This will be a domain morphing set. We need to choose the domains to act upon. In this case, I need to act on all 3 of these because I'm going to move this central box, and I need these neighbor boxes to act as transitions, which are also going to be affected by this shape optimization. So now I need to pick the grids to act upon. I'll choose these 8 corner grids. And I need to pick the direction and magnitude of the perturbation. And in this case, it's simply going to be along the x-axis, in fact, the negative x-axis. We have options to pick directions by picking existing grids. You can either pick 2 grids to pick a direction, or we could pick 3 grids to get the normal direction. In this case, it's too simple, so I'll just simply type the direction myself and the magnitude and add perturbations. And now we get 8 arrows. We have 8 perturbations on 8 grids. So that's it. I'll create another one. In this case, I want to act on these middle grids, again in the x direction with a smaller magnitude. And I want to put the same kind of perturbation, but this time in the plus x direction. So these perturbations will control the width of this domain box, and that means they'll control the width of all the structure finite elements that are inside of that box. And finally, I'll create a domain box with some perturbations to control the height. To do that, we'll pick the top. We'll go this time in the negative z direction. And in the positive z direction for the bottom. We can finish. And now we need to go back and bring the structure back. I need to actually associate the structure with the domain that I created, so I can fix that up very quickly. Select interior grids for that box and say finish. So now I've created a new domain box and some new perturbations. We can go to the Post tab. We don't have to run Genesis to preview how the shape changes are going to look. I can say oscillate, and we can animate potentially how this could change as this design variable changes. And we can see this is changing the location of this particular crossbar. Similarly, I have to change the width. We can look at the top. And this time, since I put perturbations in the middle, we're getting a quadratic variation. So we can see the shape change there. And similarly with the height, again, I had perturbations in the middle, so we get the height variation quadratically. And we can look at the ones we already had are going to act similarly on the other crossbars. We have the width of that one and the height of that particular bar. So other than that, setting up the shape domains and the shape morphing sets, we also need to set up objectives and constraints. In this particular problem, our objective is to have high natural frequencies, because for a vehicle frame, having high natural frequency gives it a good feeling when we're riding in it. It makes us feel like it's stiff in dynamics. So that's a typical objective. And the constraints are some constraints on natural frequencies and separations of natural frequencies. So these are already created in this model when I imported it. So with the definition of the shape morphing sets, we can then run Genesis. I've already run this problem, so I'm simply going to jump to import the results. And we can visualize the shape change due to optimization. We show statically, let's clear that loads. And the colors correspond to the total magnitude of the grid movement due to shape optimization. So this is how the grid moved from the initial configuration to the final optimized configuration. Or I can choose to ramp this. So we start in the initial configuration and we move to the final configuration. Or if we don't like the colors, we can simply see the elements themselves moving. And we can see we're changing the locations of some crossbars. This middle crossbar, actually the location didn't change much. Even though we gave it the design freedom, it turned out the optimizer didn't choose to move it, so it's fine where it was. We can see also how the height value is changing. For this particular, the middle member is getting a little wider. This last member, the height is getting a little bit thinner. If we show the colors, we can change to normal to surface. And this will color based on the component of the grid motion, normal to the surface of the element. So Design Studio also has other facilities for shape. For example, we could go to Analysis, Grids, select all the grids and modify. We can apply a deform result set, and we can choose that final design cycle and say Finish. And now we've actually updated our finite element model to have the new shape that the optimizer said was the best. So this really finishes up this shape example. I'd like to move on. The next type of optimization I want to consider is the topography optimization. Topography really can be thought of as a very special form of shape optimization. except all we're going to consider are moving grids normal to the surface of shells. So we have to have shell elements, and we're going to automatically create perturbations normal to that to try and create some sort of a corrugation pattern or a bead pattern that would make the shell stiffer in bending. So let's jump back into Design Studio and look at a simple topography example. Here we have a simple finite element model of the hood of a car, and we have an inner panel. The red color is a separate shell inner panel that we want to allow to have corrugations or bead patterns that will make my hood stiffer when I apply some torsion loads to it. And if we look at load cases, you can see we have two load cases. We're fixing it at the attachment points, and we're applying a load offset from the center, which would try and twist the hood. And we want the hood to feel stiff under this particular type of loading. So we will try and apply topography to this inner panel and see if we can improve the performance. So to create topography data, we simply go to the topography category. We choose the property that we want to design, and we go to the Modify Topography Design button. We have some options in defining the basic topography data. One is the shape type. We can either have a cone or line, and these pictures at the bottom are reminding us what these represent. With the line type, we're simply going to move each individual grid normal to the surface to some potential maximum height offset from the initial surface. With the cone type, we're actually going to move a whole family of grids in some basic shape, which we call cone. This is actually can be thought of as the frustum of a cone, where we cut off the very tip. And we have three parameters. We have a minimum width, we have a max height, and we have a spread. And this sort of gives us a smoother transition from where the bead is going to start and stop. And so this often will give us a nicer looking bead. So we'll use the cone pattern. We need to define these parameters, which I'll use some numbers, typical. I'm going to define a bead fraction. The bead fraction means we are going to limit the total number of grids that we want to allow to move under shape optimization. Giving a bead fraction often will give us much nicer looking beads, so we will do that. Say only allow 35% to move. And finally, I want to give an upper bound for this case. In this case, the shell's normal is pointing in the positive z direction. I only want to allow the grids to move in the negative direction, which means I want the design variables to always be negative. So if I give an upper bound of 0, I'll force the problem to only allow the beads to move into the negative direction. So with the finish, I can set up my objective. In this particular case, it's going to be to minimize strain energy of my load cases. Minimizing strain energy, just like in the topology problem, will make the structure stiffer. I'm not going to need any additional constraints for this problem. So with that, I am ready to run. I can go optimize. In this case, I'm simply going to jump to the results that I have already generated. And again, we can show the shape result by deforming the mesh according to how the shape changes. And if we color it, we can also see the blue grids, of course, were not designed, so their motion is 0 under the shape optimization. And we can see the maximum grids. If we look closely, we can sort of make out the pattern that the optimizer is trying to tell us. We want a bead along the front and along the back, and we might like to have some center bead and maybe cross beams and the sides. So this is really topography optimization. So finally, I would like to consider the last form of optimization we have in Genesis and Design Studio, which we call freeform. And this is actually the latest addition to Genesis and Design Studio. In this, it's very similar to topography in a sense, in that we're going to make many design variables and we're going to have lots of perturbations. But rather than forcing us to only look at surfaces of shells, we are going to basically consider any perturbation set. We're going to take all of those perturbations and split it so that every single perturbation gets assigned its own independent design variable. This will give us, so in a sense, freeform is to shape what topometry is to sizing. Let's jump to Design Studio and look at the freeform problem. For this to set up freeform, we simply need to create a shape morphing set. We'll make a raw set and we'll say freeform. We need to create perturbations. We want to create perturbations on the surface of this blue solid block. This blue block is solid elements. This whole structure is under some sort of torsion loads, and we would like to put some sort of surface bead on the solid blocks that will make the structure stiffer under the torsion loads. So we will create some perturbations normal to surface. We will define the magnitude. We will choose grids, all in the blue group, add perturbation. So now we've created a lot of perturbations. We also want to impose some symmetry constraints. In this case, we want to have triple mirror symmetry. So X, Y, Y, Z, Z, Y, we all have symmetry across each one of those planes. We say finish, and that sets up our freeform. And the list tells us F there, which means this morphing set is actually a freeform set. If we go to the preview, we can see that at the preview, actually all the grids move together because Design Studio is not considering the freeform aspect. But because it was marked with freeform, it means when we run Genesis, it will actually do the split and give every perturbation an independent design variable. Actually, in this case, because we have the mirror symmetry options, they won't actually all be completely independent, but we'll have some links there to enforce the symmetries. But still, we will get a large number of independent perturbations. We would set up the objective and constraints as we have done in other problems. And in this case, I'll jump to load the results. And we can show the shape change pattern that we get with the freeform. And we can see the triple mirror symmetry. So I'm afraid I'm running short of time, so that will have to finish up this freeform problem, and I will now go to my conclusions. What I hope that you were able to see in my demonstrations is that Design Studio is easy to learn. We have lots of built-in trails or wizards for all of the editing capabilities that sort of guide you to what data you need to enter and when you enter it. And we try to make the interface as consistent as possible. So once you do learn how to go through one trail, say the sizing trail, it's not a really big deal to go and look at a different trail, even a completely different type, like the shape trail, because the way the wizards go is very similar. Second, Design Studio is easy to use. We try to minimize the number of mouse clicks you have to perform in order to create the type of data that is needed for the optimization problems. And we have shortcuts for the common tasks. For example, for sizing of shelves, we have the quick sizing trail, which makes it very quick to create lots of design variables for lots of different shelf properties. And finally, what might not have been as evident in my demonstrations is that Design Studio is very powerful. The models that I was showing were all what I would call toy problems, and they were not actually representative of the real models that people are using in industry today. But Design Studio can handle very large models. Design Studio can also handle all of the design options available in Genesis. That means that you will never have to go and actually hand edit the Genesis input file to change some data or to add something that Design Studio didn't cover. Design Studio covers it all. So that really finishes up my webinar. I would like to, before I get into questions, I would like to make some announcements. Next month, we are going to have some workshops in our offices here in Novi, Michigan. We'll have 2 one-day workshops covering Genesis and Design Studio and how to link nonlinear analysis code with Genesis optimization, so-called ESL method. That will be next month, July 21st and 22nd. So if you are going to be in the Michigan area then, we would encourage you to register for our workshops. You can find more information on our website about that. Second, we will have another webinar in our webinar series next month, July 28th. The topic will be Design Process Automation with Visual Doc. So we would hope that you will sign up for our next webinar in the series. We'll send out email announcements for that, or you can find information on our website next week about the webinar. So with that, I'll turn it back over to Fanny, and we can see if he has questions that he needs me to address.